Chapter 10, we will look at the idea of chemical bonding, and in this segment we will look at the first three sections of Chapter 10, dealing with the idea of how bonding models were used to develop drugs to combat AIDS. We will look at how we represent valence electrons that we learned about with electron configurations using dots around an elemental symbol, and then we will look at how these valence electrons in these drawings with the dots represent something known as a Lewis structure, and we can show for ionic compounds how electrons get transferred. In section 1, talks about how bonding models were used to develop AIDS drugs. So back in 1989, the structure of HIV protease was determined by researchers. This is the protein synthesized by the human immunodeficiency virus, so the one that causes AIDS. They used bonding theories, which are models that predict how atoms will bond together to form molecules, in order to carry out simulations on how potential drugs would interact with the protease. So they were able to make predictions on what drugs would be effective to combat this protease and which ones would not. And if you look at the picture shown here, the gold structure that looks sort of like a big long maze of gold ribbon represents the HIV protease, and then the molecule shown in the center right here with the red and the white with the structure in the middle is indinavir. So that was a protease inhibitor that was designed and tested to see how it would interact with that protease. And what they discovered was that without the HIV protease, the HIV could not spread itself in the human body. The virus was not able to replicate itself, and so even though an individual was HIV positive, they would never develop full-blown AIDS. So with this knowledge, drug companies were able to design a molecule that could basically disable the protease by sticking to the working part of the molecule, the active site. They were able to focus their study on the area that really mattered. And by the early 90s, companies had developed several drug molecules that would inhibit the action of the protease, so protease inhibitors, therefore. Got to the point where they were able to run human trials, and in these trials, these protease inhibitors combined with other drugs were able to decrease the viral count for individuals who had full-blown HIV. And it reduced them to the point that the HIV was undetectable. So the drugs were not able to cure AIDS. Individuals will still carry that HIV infection, but if they remain on these medications, it suppresses the action of the HIV molecules, and these individuals can expect to live a nearly normal life. So how are these bonding theories applied? How did they come into play? Well, bonding theories are able to predict how atoms bond together to form compounds, and they can predict what combination of atoms will form compounds, which ones will not. So for example, bonding theory can explain for us why the formula for table salt is NaCl, sodium, 1 sodium to 1 chlorine, and not NaCl2. Why can it not be, Na2Cl? Why is water H2O and not H3O or HO? Okay. Bonding theories also explain the shape of a molecule, which in turn can tell you much about their physical and chemical properties and how they're going to interact with other molecules. When we talk about bonding theories, we have to look at one called the Lewis theory. Lewis theory is probably the most prevalent that we see of the bonding theories. It is named after G.N. Lewis, who is an American chemist who developed this system of representing shapes and valence electrons in molecules. And the idea in Lewis theory is that we're going to represent electrons as dots. So for every electron you have, you will draw it as a dot, and you will then draw what is known as a dot structure or a Lewis structure that represents a particular molecule. And then these structures can be used to make predictions. And there's a lot of power in those predictions. Lewis theory can determine whether a particular set of atoms will form a stable molecule or whether they'll be unstable. And if it's a stable molecule, what is that molecule going to look like? How might it interact with another molecule? Modern chemists have much more advanced bonding theories to refine this idea, to better predict molecular properties, but Lewis theory, as basic as it is, remains the simplest method to make a quick and dirty back-of-the-envelope prediction about particular molecules. So unless you need a very high level of information about the structure of a molecule, the bonding angles of a molecule, Lewis theory is probably going to get you where you need to be. In Lewis theory, the valence electrons for main group elements will be represented as dots surrounding the symbol of the element. So we'll just write the symbols such as sodium, and then we will put in the valence electron dots. Now, this is what we call a Lewis structure or a dot structure, and it will be based on the knowledge of the number of valence electrons. So keep in mind that the number of valence electrons for any main group element, not the transitions, but the main groups, will be equal to the group number of the element, with the exception of helium. It's in group 8A, but it only has 2 valence electrons in it. So if we look at sodium, for example, that I showed you, I would write the symbol for sodium. I would look at its position in the periodic table, which is in group 1A. That tells me that it has 1 valence electron. So I would draw that 1 valence electron as just a dot. And a little bit of trouble drawing a dot here. So that's to represent just a dot around the sodium. And you can put it, if you think of the symbol as being in a box, you have 4 sides on the box. You can put that dot on any one of the 4 sides of the box that you want. So let's look at another example. If we look at oxygen, if we look at the electron configuration of oxygen, it is 1s2, 2s2, 2p4. Now, the valence electrons, remember, are the outermost, so they're the ones in the highest orbital, the highest shell, which is 2. So if I look, I have 2 s2s and 2 p4s. That's a total of 6. Okay, that corresponds to oxygen's position in the periodic table. It's in column 6A. So the Lewis structure would have 6 dots around it. I would draw the symbol for oxygen, and then I start putting the dots. So notice the way we do this. If you think of the symbol, such as oxygen, as being in a box, what you're going to do is when you start putting in dots, here's 1, 2, 3, 4. I start by putting 1 on each of the 4 sides. So just as we said with electron configuration that we put them in one at a time, then we go back and double up. I've put in 1 on each of the 4 sides, okay, the 4 spaces that are available. Now I need to go back and put in 2 more, so I start pairing them up. And it doesn't matter where you pair them up. That's how they show it. You'd get the same thing if you put 2 here and 2 here and then 1 on each of the other sides. It doesn't really matter as long as there are 6 and you have them paired up only when necessary. All right, so as we said, each dot represents 1 valence electron, and we place them around the symbol with a maximum of 2 dots per side. The location is not critical, but fill them in singly first and then start pairing them up, with the exception of helium, which we'll look at in a minute. Okay, it's important to follow this convention when you're looking at the homework and doing the homework. Otherwise, it may not match up to what you see. So for example, if you have 4 valence electrons around some symbol and you just go ahead and pair them up, that will be counted wrong. You would have to start out by putting 1 each around the 4 sides. All right, so here are the Lewis structures for the period 2 elements. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and you can see going from left to right, the number of valence electrons increases by 1 each time. And you can see how they've arranged them around the symbols. Notice that for the first 4, the dots get placed singly. We don't start pairing them up until we get to the fifth one where we have to go back and start pairing. Also notice atoms that have 8 valence electrons, such as neon here, these are stable, okay, easy to identify using a Lewis structure because they already have 8 dots around them. They have an octet. That is what everything is striving to match. They're trying to look like the Lewis structure for those noble gases. So looking at another example, if we write the Lewis structure for phosphorus, if we look at phosphorus's position in the periodic table, it is in group 5A, so that tells us that it has 5 valence electrons. Okay, we represent those as 5 dots around the symbol for phosphorus, just as we see here. We put the letter P, we start by putting 1, 2, 3, 4 dots, and then we go back and pair up the 5th one. Keep in mind that helium is an exception. Okay, so its electron configuration is only 1s2, so it only has 2 electrons. Now, those 2 dots, those duets, that is a stable electron configuration, and they are paired because there is only one shell, one orbital for those electrons to be in. That 1s is the only available place for them. So rather than drawing helium with a dot on one side and a dot on the other, okay, we are going to put them together. That's the only case where you go ahead and pair them up because that's the only place they can go. Now, how do we use this idea of these Lewis structures for elements to represent chemical bonds? How do we bring them together? In Lewis theory, a chemical bond is going to be the sharing or transfer of electrons between these atoms to get that stable electron configuration, to get that noble gas configuration. So what we will look at is whether or not electrons are simply transferred from one structure to the other, in which case we are looking at an ionic bond. Okay, so transfer is ionic bond, or if the structures are going to share their electrons between them, in which case it's a covalent bond. So we've talked about this a little bit. Now we want to look at visual representations of it. So how can we actually predict, instead of just saying, okay, this is where it is on the periodic table, that's what it's going to do. Why is it doing that? That's what we want to look at. Okay, what they're trying to do, whether it be ionic bond or covalent bond, they are trying to get a stable electron configuration. That is the key. In a stable configuration, remember, other than the exception of helium, usually you're going to have 8 electrons in the outermost or valence shell. Okay, so that is known as the octet rule. So when you are carrying out chemical bonding, atoms are going to either transfer or share electrons in order to get outer shells that have 8 electrons. That's the stable point. Now the octet rule generally will apply to all main group elements. Now there are some exceptions. Hydrogen is an exception because it is so small, it really has only one space. So hydrogen and helium. Helium doesn't undergo bonding. Lithium is an exception, and beryllium. And notice these are very small atoms very early on in the periodic table. And some of it just has to do with the amount of space. All right, so for those 3, remember those 3 because they will be in bonding, hydrogen, lithium, and beryllium. Those elements can achieve stability with only 2 electrons in the outermost shell. Okay, everybody else gets 8. Hydrogen, lithium, and beryllium get 2. So let's start by looking at ionic compounds in this section. So we are looking at electrons being transferred, and that occurs, as we've said many times before, when metals bond with nonmetals. So we've said that the metal becomes a cation, the nonmetal becomes an anion. You know all this already. And the resulting difference in charge between the cation and the anion results in an attraction that forms an ionic compound. So how do we visually represent this in Lewis theory? We do this by physically moving the electron dots from the metal to the non-metal. So we are going to redraw their Lewis structures to show the movement of those electrons. For example, if I look at potassium and chlorine, if I draw the Lewis structure for potassium, I see that it has one valence electron, so I have one dot. When I look at chlorine, it has 7 valence electrons, group 7A, so it has 7 dots around it. What I am then going to do is show the transfer of this one electron. If this one can transfer its electron over to chlorine, now potassium has emptied its outermost shell, drops back to an inner shell which is already full, so it's good to go. Chlorine gains an electron which fills the shell that it's already working on. It has a full octet, so everybody's happy. So representing that visually, here's what I start with. What I end with, here's the Lewis symbol, Lewis structure for potassium, minus the electron, but showing that I have a charge. So when you're doing this for ionic compounds, you have to include the charge that is created on the ion by the movement of those electrons. This is showing that an electron has been removed. And then the chlorine, okay, here's the electron that was gained from the potassium. I put a charge on there, and notice that it's in brackets, okay? So we need to include the brackets around. If I don't have any electrons in it, you can see potassium doesn't have a bracket around it. You could put a bracket around the potassium. That would be fine, just with no dots on the inside. But when you do have the dots, you do need to bracket it and then put the charge on the outside, okay, to indicate that this is an ion. So the transfer of the electrons, just to summarize, gives the chlorine an octet, leaves the potassium with an octet from the previous shell. Okay, so once that shell drops away, once that electron got kicked out, that shell is gone, and so it drops back to the next inner shell, and that becomes the new valence shell. Okay, we said the potassium becomes positively charged, the chlorine becomes negatively charged. They attract one another, forming this compound. Okay, now these are meant to be together. The anion is usually written within brackets. You could show the brackets on the cation as well, not necessary. Charges must be shown. Okay, now when you are doing the mastering homework, the brackets will not be shown. That's just something that they can't work into the program. But be aware that normal convention would be that you would put brackets around your anion to kind of contain all those electrons. Looking at another example, if you wanted to write the Lewis structure for magnesium oxide. So if I start with the Lewis structure for magnesium, its position in the periodic table is in group 2A, so it has 2 valence electrons. Oxygen is in group 6A, so I would give it 6 valence electrons. There's all my dots. Now I can visually see what's going to be the easiest way to get these to either have no electrons or 8 electrons. Well, it's going to be to transfer the 2 electrons from the magnesium over to the oxygen. Okay, so magnesium loses 2 valence electrons. We end up with a 2+ charge here. Oxygen gains those 2, and it has a 2- charge. Excuse me, this is how then I would visually represent the Lewis structure for this compound. Ionic compounds will always have charges on them. That's how you're going to know in a Lewis structure that you're dealing with an ionic compound and not a covalent compound. All right. Now we can also use Lewis theory to predict what the correct chemical formula would be for an ionic compound. So for example, if we take sodium and sulfur and we look at their Lewis structures, shown here, 1 valence electron on sodium and 6 on sulfur. Okay, now sodium loses 1 valence electron to get an octet. Sulfur needs to gain 2. So this is what's telling me it's not going to work to put just 1 sodium with 1 sulfur. I can go ahead and transfer that. Now sodium is happy. I end up with just Na+ for my structure. But now sulfur in this case, see if I can put my dots in. Okay, I put 2 on the bottom, so I'll put just 1 at the top, changed it up a little. So now what I'm getting is just sulfur 1-, but I still need another electron. I'm still missing an electron in there. So what I need is another one of these sodiums that can donate another electron. Okay, so that's what's telling me I need 2 sodium atoms for every 1 sulfur atom. And then the Lewis structure would look like this. And the correct formula then would be Na2S. So that's an overview of Lewis structures and how to write Lewis structures for ionic compounds. In the next section, we'll look at what happens when we are going to share electrons in covalent bonds, how to write the Lewis structures for those, and then we'll look at something known as resonance.